posted a response. I think the TAs posted a response, but it's important to understand just exactly how these things are supposed to be used. Now, another thing is, I think some folks, I've looked at some of the class tables that people have generated, the type tables, the V tables, and the preceding information some people have generated. Also, string and int objects that they've assembled into the data sections of their code. And I've noticed that you may not all be aware of exactly how to read or how to construct objects that are described in C++. It's exactly as in, I mean, this is actually a case where the lecture was applicable to what happens in real life, amazingly enough. So what usually happens is that you see, oops, nope, sorry, I don't have any chalk this time. Boy, they keep depleting the supply. And they probably don't have any over here. All right, fine. We will have to use more sophisticated visual techniques, I guess, which may actually help the poor folks at home. So if you see something like this, for example, class, I forget what the thing is, class py type object, for example, and you see public py object here. When you see that, it tells you that before, let's see what's in here. I think there's an int sig size here. This is telling you that that at the very beginning of this type object, there is a py object. So you have to go back and you have to look in py object and see what fields are there. If I were writing this in C, then every single one of these types would have all the fields of its parent type in it as well. Since I'm writing in C++, I get two advantages. One, I don't have to write that, and two, I don't get type errors because of illicit conversions from one type to another type that just happens to look at the same at the beginning, which is what you have to do in C. So please make sure you understand that when you put out when you output a type object, for example, or a string object, which is also a kind of object, py object, make sure you understand that you've got to have those first parts in there as well. The assembler does not understand. Oh, here's chalk. The assembler does not understand inheritance. You have to do that by hand when you're doing assembler, just as you would if you were having to output C. Okay, so that's I noticed. So I noticed those two problems in particular. What do I do with these? What do I do with these virtual tables? And what do I do with these? Yes, why do I need these virtual tables? And how do I lay out data in one of these objects represented in C++? How do I lay it out in memory? So make sure, try to get those two things straight. They seem to be giving some people problems. And let me repeat something I said before. If you see .word anywhere in your assembler output, you're doing something wrong. It should probably be .long. .word takes us back to the good old days of the early 8086 and 8088 and so forth, when all data was 16 bits, because that's what the processor was best at, and Bill Gates thought, why would anyone need more than 65K? Do be sure that you make sure that you get your constants the right length. All right, further questions that have come up about the project? Yeah. Yes?
It seems like comparison should be included in Why not, right?
Well, they all output pybool. I don't know what you mean. Or what are you getting at, I guess, is the issue here.
Well, in expressions.cc,
Well, that's because comparisons are handled differently. I mean, if you see, so if you're just doing if A less than B, everything's fine. You can just do that the same way you would do a binary node. But unfortunately, you can, or fortunately for the programmer, I can also do that. And this has an entirely different meaning. This does not mean compute A less than B and then take that result and compare it to C. That will give you the wrong answer. It means take A less than B. If the result is true, then take B and compare it to C. So that's
a string of those however long you want.
That's right. So it's true that in the middle here, when you're actually doing the comparisons, you will have to do exactly the same thing as you do in binary nodes. And you might notice that there is machinery actually in, there is some machinery. It doesn't quite extend to comparisons, but it gives you the idea. There are things in the way that the project's 3 skeleton is set up, so that things that look different, but really generate the same code or have the same semantics, have a few extra methods to help. So you have something that says get the function that's going to be called by this node, get the operands that are going to be called by this node, so that you can handle function calls and binary operators using similar. You can have common code for doing those things, and you can extend this maybe to help a little bit with comparisons. So anyway, but just remember that there is that funny little glitch about comparisons. It's not quite the same as binary operators. Okay, why don't we get down to business in that case, or other business. All right. Now, so we talked about optimization. I went over briefly, or surface level. This is just an introduction after all. Optimization at the local level. Now let's see what the compilers do about larger optimizations. Now, global optimization, which means not global, but within a given intra-procedural optimization, in which we look at a complete control flow graph for a single procedure and we optimize it. And I have used the term galactic optimization. That's a lie. I think it was one of my master's students who did that many years ago. And by the way, there are cases where galactic optimization can get you big payoffs, although it's disappointing, actually, how seldom that is. So what we have to do in order to be able to apply optimizations like the ones that we did on local variables is we have to do some additional analysis of the control flow graph to figure out things like what variables are live and so forth. And in order to answer this question of how can we do some of these optimizations like common subexpression elimination or analogs of them across basic blocks. So if we take a look at simple copy propagation, here is an example where we have an assignment to X, and later on in the program we have a use of X, where before we just changed the X to the thing that was assigned to it. And it's still valid here. We could still do that. We could simply replace this X here, the second X, with a 3, and everything would be fine. Unfortunately, if we insert an assignment to X in either of the two branches of the if, obviously, note this assignment, this optimization is no longer valid. So we have to somehow figure out when we can really do this. So we have to do, as I said, we have to do some analysis. We have to look, in general, we have to look at a large number of paths, or at least multiple paths, all possible paths between two statements before we can make any definitive statement about whether a variable has been assigned to. before getting there. And this requires that we look at the entire flow graph. So the problem is, of course, that a lot of the properties that we're interested in are undecidable. Or we might be interested in are undecidable. So what happens is we have to err on the side of being conservative. And this business about but not cowardly means that if you're too conservative, then you simply don't do anything and you get a big and slow program. So, yes, well, that's true. Some have said that the interesting properties are undecidable, such as, for example, is the output from this program, from this function, a calculatable constant? It's undecidable. So, or does it halt? That's an interesting question. Does it deadlock? Another potentially interesting question. Excuse me. We'd like to know if something is positive. Indeed, there is a way in the field of program verification, you can actually extend type checking so that you not only have programs that take integers and return integers, you have programs whose type is they are the type of program that takes an integer and returns the factorial of that integer. And then if the program type checks, it means that it's right. It means that the thing actually does the right calculation. And of course, yes, you can define such a type system, and of course it is undecidable, and therefore not very useful in practice. Now, if we don't have any loops, then things become considerably easier, because if you don't have loops, you can look at all possible paths, and it's a finite number, and everything is fine. So, so basically, let's talk a little bit about what conservatism is in this case, because around Berkeley you might expect that it's unpopular, but in fact in program verification it's kind of important. So if you know that you can either know that, I'm starting to sound like Rumsfeld, there are known knowns and unknown knowns and there are unknown unknowns and known unknowns and so forth. Well, you can know if a property is definitely true, and if it's definitely true, and that property is a hypothesis you need for an optimization, you can apply it. And then if you don't know that something is true, you can say, well, all right, fine. In this case, we don't apply the optimization, and that's basically conservative because the optimization in the first place is not supposed to change what the program does. So, not applying it shouldn't change what the program does either. So it should be okay. And therefore, this whole thing is to figure out is to know as much as possible, and to admit when you don't. And of course to be somewhat diligent, so you don't just say it all the time. So let's take a look at an example. Constant propagation, globally this time. And we'll look one variable at a time. I mean, in practice you have to bunch these things up a little bit perhaps, but let's look one variable at a time. So what we're going to do is, in effect, we're going to interpret the program in a funny sort of way, except with a very restricted set of possible values. So instead of, if we're talking about an integer variable, instead of saying that the variable has possible values -1, 0, and so forth, we'll give it only 3 values in our program. It can have, we can have the value that so far at any given point, and we're talking about a value at any given point in the program, we can have a value that I'll call hash, or bottom, meaning that we haven't gotten to that point in the program yet. Now, in fact, the variable may end up having hash at the end of the program if, in fact, that statement is unreachable. But at the outset, we conservatively, we might assume that not conservatively, but we might assume that possibly the variable is never reached, or that is never assigned to. we can know that the variable has a particular value. So that's another possibility. So we have one of these for each possible constant value of the variable. And then the other possibility will be that the variable has some value, but we don't know what. It could be any one of a number of different values. So those are our three categories of value. Actually, there are an infinite number of constant values, but we'll see why these extra two values, hash and top, bottom and top, are important. So here is a graph showing the value of x at each point in this program. So we start up at the top. X has some value. We don't know what it is. So we assume initially that x has some value. And we denote that fact by just saying x is top, some value. After an assignment to x, obviously we know that x has the value 3. And therefore, since b greater than 0, that test doesn't change it, we know that x is greater than 3 immediately after that. And therefore, we know that it's true at the beginning of these two branches of the if statement. So it propagates down as you see. X remains 3 until we get to, except on the left there, where it gets assigned 4. And therefore, when these two branches come together here, when they join right there, since x has two different values on the two branches, we will combine that by saying x's value is some constant, star, top. And therefore, at this point, when we come to this point, we see that the value of x is some unknown value, and therefore we cannot apply constant propagation. Now, obviously, on the other hand, another possibility is that we don't have this statement here, in which case both branches would come in here and both would say x equals 3, and so we'd say, okay, fine, I believe you, x equals 3. And at that point we could do constant propagation. Or possibly even both branches assign 3 to x, or 4 to x. Both branches assign 4 to x, in which case we come down here and we see, well, x is equal to 4 on both branches, therefore its combined value is 4 also. So this is just like, so basically we have these states. We have no data yet, this specific constant or some unknown constant, and we put those together. Okay, so now, given this information, we can now easily determine, we can do constant propagation very easily. We just do it in the usual sense. And so the problem is, okay, fine, how do you compute this? So let's introduce here's a concept that actually applies quite a bit to this kind of problem. We call it the concept of a transfer function. So we have some property, and every different kind of statement will operate on that property in some way. And we call that operation a transfer function. And it tells us, and that tells us how each statement modifies the information that we're interested in, and how we transfer it to the next statement. Now, so what we end up with, we'll just use this notation C in and C out to refer to, for example, or things subscripted within and things subscripted without, to mean the value of the property before and after a given statement, a given statement S. Right? I don't know why the X is uppercase in this case. It shouldn't be. All right, fine. So let's look at constant propagation in particular. So we're looking at, in general, we'll have a statement, and we'll have immediate predecessors of that statement. Inside a basic block, there's just one, and when we have several blocks, when we have a join, a confluence of things, then we'll have several of them, and we'll have to figure out how to combine them. So we'll put a few rules in place. Now, here's what we're moving toward here. I'm going to we're going to come up with some transfer functions that tell you how to convert these values at each point in the graph, how each statement converts them. Then we will start from some initial graph that has in which we make guesses as to the values of all of the variables at each point in the program. And then we will apply the rules, one rule at a time, until things stop changing. So you've seen this before. It's called a fixed point computation. And when we're done, we will have conservative information that we want. So our first rule of propagation will be that if you have a bunch of statements up here, or a bunch of predecessors, and they have values like this, if any one of those values is star, then the value at the beginning of the statement is star. So if any predecessor of a statement has star as its value, then star is the value at the beginning of the statement. We take star to be the value at the beginning of the statement. Right? So that's rule number one. Rule number two is that otherwise, if we have two different constants as predecessors, then the value at the beginning of the block of the block that is preceded is star. Right? In other words, there is some value we don't know, but it could be different things. So we definitely don't know. We know all we can say is that it has a value. Another possibility is that all the nodes are either all the predecessors either have the value of the variable being a particular constant, one particular constant, or unreached. In other words, we don't have a value there yet. In which case, we will tentatively say that the value at the beginning of this node here is C, is that shared value. So you'll notice this is not a conservative thing in and of itself, because it's possible that we will discover, oh, wait a minute, this predecessor node up here actually does get a value eventually, and it's not the same as C. So that might happen, and that's why we have to iterate this thing. That's why we have to repeat this thing until done. And if everything is unreached, then we will say that the value of x here is unreached. So we will say that the beginning of this statement is unreached, and its value is this bottom thing. Okay, now, so that's telling me how to relate the outs from the predecessor statements to the in for a given statement. And now we have to figure out how to transfer, or in other words, how to transfer across arrows, basically. And now we have to figure out how to transfer across individual statements. So we need a local thing for each individual kind of statement. So here's the first thing. If S is some statement that, yes, okay. So if S is just some statement that doesn't that hasn't been reached yet, then the not reached yet property propagates through the statement. Right? So, right? That's the first rule. If we have an assignment to x of a particular constant, then the value at the end will be afterwards will be that constant. If we have something else, now here I say any function call, but let's just say any. Let's say this will also include all other kinds of statements that assign to x. Then we conservatively assume that we don't know the value of x at the end, although it has some value. So we say, okay, fine, it's going to be star, and that's assuming that the value at the beginning is something other than hash mark. Right? If we assign to some different variable y, then there's no effect on the value of x, so we simply propagate it right through. And Rule 9, there is no Rule 9. Okay, so now you could imagine that we put in a few other rules as well. For example, we could do a little constant folding there. So if you have a known function or binary operator of two known constants, then you could assign a known constant. But let's just restrict ourselves to simple assignments. So we're iterating to a fixed point, a very common property of these algorithms. And we keep current approximations to the property we're computing at each point in the program, and then we set things up. So we have to have some reasonable initial thing. So the initial thing in this case will be that at the beginning of the program, x has an unknown value and everywhere else hasn't been reached yet. And then we just apply all these rules until nothing changes. And it's possible to do this better. For example, if you change a node causing its output to change, that might very well change the value of the next node. So probably it's a good idea to go through the graph in some sort of a depth-first search. Yes, but let's not worry about that. That's true. It's true, but it's sort of more of an advanced topic, how to be clever about this. Let's just at the moment work on concepts. So let's look at an example. Here is the starting position. Let's see what I do. The first thing I do is I propagate 3 to these 2 locations, doing a couple of applications of the rule. And that causes 3 to go to all of those locations by a few more applications of the rule. And now we have x equals 3 on 2 branches coming in here, so we can put 3 on all of those. All right. Now at this point, let's see what happens. We now have 3 coming in here. It looks like at this point there are no further changes if we keep doing this. If we keep applying the rules everywhere, there are no further changes, so we're done in this case. Okay. Now let's look at this same thing, this time with this 4 in one branch and not in the other, the example we did before. And so here we get the first step is the same as before. Second step is not quite the same as before because at the end of this, applying the rules about, so this rule is we're assigning to y so the value doesn't change. And this rule is we're assigning to x so the value does change to 4. Now we have 2 nodes coming in here, but they have 2 different constant values. So applying one of the other rules tells us that these are all star. Now we have the input to this block here. We see that the input to this block now contains whereas before it contained a hash coming in on this side. Now it contains a star. So we have 3 versus star, and the rule tells us that these now must become star. And at this point, the iteration stops. So actually, in this case, not only can't we replace x with 4 here, but if we had a statement here that used x, we couldn't replace x with 3. We couldn't replace x with 3 here either. Right, so and all of that information gets propagated this way. Now here is another example. What are we doing here? Oh yes, here I change x to 4 after assigning here. Okay, so let's see what happens. In this case, everything is the same as the first example, except that right down here we end up at the end of this loop, x is equal to 4 rather than 3. And now we have the situation where here, this block right here has a 3 coming in here and a 4 coming in here, so it's now star. And now we have a situation where this block has a 3 coming in here and a star coming in here, so it's now star also. And again, we cannot replace the x. So in this is a case where you have a loop and you have to keep iterating in order to get back to it. So it's actually, the order is irrelevant. I did it in a semi-clever order in the lecture slides, and you can too. I mean, it doesn't really matter. And the purpose, as we see, these examples show you the purpose of having this hash value is that we don't, is to avoid being overly conservative. So we don't decide anything for sure until a statement that is not reached or a branch that's not taken isn't going to affect the final outcome. So you don't change the final outcome until you get some actual value on that branch. Okay, so now let's actually, at this point, let's take a brief break and do some consolidation. So questions so far? I hope this is pretty intuitive stuff, even if we are doing a little bit of abstract algebra here. Fine, let's take a break. Yes.
Let's say X was the third volatile, for multi-threaded.
It was
volatile, the C++.
Volatile, yes.
Volatile, yeah. Then would these all be stars then?
Yeah, you basically have to assume that X is being changed at every point in the program. So the rules in that case would change. So X would always be star, regardless. And yeah, you have to. That's an interesting question. Yes, that is one of the problems. That's why you try to avoid. That's why you avoid making things volatile. Unless you need it. So I mean, think about a busy wait, which is where you use these things. So while lock equals 0, repeat. So obviously, analysis would tell you that the value of X never changes. So you have to use the fact that you don't know what that value is to tell you that you can't get rid of the X equal less than 0.
My question is, so are we in the project, are we supposed to avoid changing the runtime?
If you need to, you can.
Okay.
And I should make a little announcement about what you have to do if you do that.
Okay.
Like you have to include it in your hand-in, otherwise we won't. Mm-hmm. No.
I know in my bug submit I sent the runtime in. And I guess I added a method into the runtime because I really didn't understand.
That was the get method. That was the get index.
Yeah. How to manipulate the stack.
Yeah. That is not the. That particular method was perhaps not the best. I mean, there are things that you might want to do. Mm-hmm. Like people have asked about, can I have a make string? Well,
yeah. I mean, I was just kind of playing around with it. So in general, we should try to not.
Yeah, but I mean, for one thing, it's a slight management.
Hard to debug.
Maintenance headache, because if I change the runtime, which I don't do very often, but occasionally I do, and you miss it, then all of a sudden.
Okay.
There'll be something with it.
All right, thank you.
Yeah. Okay, let's start up again. So you might guess that a lot of these analyses, given that this transfer function idea means that we're going to see a lot of the same stuff over and over again with a slightly different cast each time. So it's nice to get some generalization here. So this structure that we use for the abstract values of variables is called a lattice. Actually, it's a complete lattice, in fact, in this case, meaning that it looks like this. It looks sort of lattice-like. There are some operations on lattices for least upper bound or greatest lower bound. You'll often see these symbols that look like a squared U for least upper bound and a get those mixed. Yes, for least upper bound and an upside down square U for a greatest lower bound. but we'll just use least upper bound and greatest lower bound. So the rule for Cn, now we can just have one rule for computing Cn from all the predecessors, from all the outs of the predecessors, which is that you take the least upper bound of all the predecessors. So work it out, you'll see that it works. So if one of the predecessors has a constant value and everything else is hash, then the least upper bound is that constant value. So if one of the predecessors has, say, -1 and everything else is hash, then the least upper bound of -1 and a bunch of hashes is -1. If one of them has -1 and one of them has 0, then the least upper bound of those two is star, and so forth. So that's sort of the application of discrete math to this. And now the interesting thing is, so we say repeat until done, all right? Of course, how do we know that things are going to get done? I mean, what kind of an argument would you make that says why things get done? Well, it's very simple. If things are always moving up the lattice or alternatively down the lattice, you can do it either way. If things are moving up the lattice, and that's all transfer, and you can show that all transfer functions move things up the lattice, then this lattice has an interesting property, which is the depth is finite. And therefore, and as long as you make sure that that's true, obviously if you have an infinite lattice, infinitely deep lattice, you have trouble. But if it isn't, then as long as it's finite like that, you know that your algorithm has to stop. And in fact, you can even figure out how long it's going to take to stop. How long is it going to take to stop? Do I say that? Yes, that's right. Here it is. Yes, how long does it take to stop? Well, it's got to be it's going to be the depth of the lattice, in this case 2, times the number of times basically the number of times you could imply it. So there you are. So it's pretty it's pretty good. Of course, you can still have very large constants, which is the problem. Let's look at another analysis. This is liveness. Is a variable alive? You know, we've applied this to register allocation and things like this. In this case, we'd like to get rid of dead code once we've got all of these, once we know what the values of variables are. So let's see how we could do that. How can we find out that the assignment x gets 3 is yes? How can we yes? After we do copy propagation, how can we see that x equals 3 up here? This assignment up here is no longer necessary. So what we'd like to do is compute live variables, live or dead. So and the thing that we have to look for is there a statement that uses it, and is it possible to reach that statement from the current point in the program? So that's the information we'd like to get. So this time we'll use a 2-value lattice, false and true. True meaning reachable. True meaning reachable, I guess, and false meaning not reachable. And we'll do things a little bit differently, although the principle is still the same. We're going to do things backwards. Now here are the rules. This time we'll go from outputs to inputs. We'll go backwards to the control flow graph, which makes sense because a variable is live as long as it will be used later, so it makes sense to go this way. Okay, so here we are, and if the variable, and the basic idea is if the variable is used on any of these branches, then we say that it's live at the end of this predecessor statement P. So the least upper bound operation, in other words, in this case, is going to be is going to be the logical OR of the liveness of the successors, and that's how we'll do it. And then the local rule for individual statements is that if you have a statement that uses x, then regardless of what its value might have been afterwards, x will now be alive above that statement. All right. And if we don't use x, if we assign to x, then its value above the statement it will be false because we don't need it. We don't need it in order to assign to it. So assuming that e does not use the value of x is dead up above this statement. And finally, a statement that wrong direction. And finally, a statement that doesn't use x is simply preserves its value. So there you are. That's all we need. So we'll assume initially that non-conservatively that the value x is not used anywhere, so that all of them can be used, and then we will repeat this rule at the exit to the program, assuming that x is not going to be used elsewhere in the program if we know that someplace. Like, for example, it's a local variable to x, so at the end of the flow graph we can get rid of it. We'll just initialize that value to false. And there we are. So here's an example. Here's a program, and with the initial values of everything. And let's see what happens. Here we have an assignment to the first time that x gets used, or the last time that x gets used is right here. So above this point, x will be necessary. All right? So we keep going. That propagates then to, now I go backwards again. That propagates to these statements. And now, as a result of that, it propagates not only to these two statements up here, but also because of this branch right here, it propagates back up to here. So now x is, so at this point, x is true just about everywhere except at the very beginning of the program and right here at this assignment. So since x is dead at this point, we know that we can get rid, since x is dead at this point, we know that we can get rid of that variable, or that statement. All right. So, guaranteed, and we can eliminate the dead code. Of course, as soon as we eliminate the dead code, the result will be what? So a is equal to 2 times x. I think, well, does it end at that point? I guess it ends at that point. Let's see. X will be needed. Actually, no. As soon as we get rid of this, if we get rid of this statement, then x will not be needed here, but it will be needed here. So I guess things do continue to be the same. Okay. Same termination thing. So we've seen 2 examples. One, we're doing a forward pass or forward passes through the graph from outs to ins, and another one where we're going backwards to the graph. They're both the same idea. It's both the same idea, and we have in both cases we have this lattice. We have the transfer function. We're doing least upper bounds for converting predecessors to or for transferring predecessors to successors, or vice versa. Now let's look at, we had this idea for common subexpression elimination, which was to convert everything so that there's a single assignment to each variable in the program, and it had certain advantages for describing the common subexpression example. So unfortunately, it doesn't easily apply when you're looking at global analyses. So you get this situation where I assign 2 different values to x. So what do? I can't just say, well, x1 is equal to a here, x2 is equal to b here, and what happens when I need x down here? What do I refer to, x1 or x2? So we put in a mathematical kludge. And that's what it is. we introduce a funny function that we call the phi function. It's a complete fiction. It makes absolutely no sense. You can't implement it, but it works for the analysis. Basically, this thing takes the possible the various possible values of x, combines them, and by some magic oracle figures out which one of them applies and assigns it into x3. So with this function now, we can put everything into single static form. And there are ways of introducing these things so you don't put in too many of them, because of course when you put one in, it does disrupt things a little bit. So we can see, is this what we've done here? Yes. So what happens is with this, we can now do global common subexpression elimination. Because that means that when we come down to a statement, we look to see, okay, I'm using the variable x3 here. It has some operands, and I can now tell whether those operands across the entire control flow graph come from the same assignment to x, to the same value of x. And I can then apply global subexpression elimination directly. So it's kind of interesting. All right, so basically, let's just sum up here. So we have these two analyses. It's both basically the same thing in both cases. You just reverse the arrows first. And you can do lots of things. The homework has an example or two. You can do lots of things with this same flavor. And all you have to do is come up with an analysis that you want to do, an appropriate lattice of values that has the right properties, and you just perform you figure out what the transfer functions are and perform an iteration, and you can get all kinds of information, not just simple true-false values, but things such as what is the statement from which this value came, that sort of thing as well. Okay, so at that point, that's our brief overview for the purposes of this course of global optimization. There's certainly an awful lot more in this subject. The books are very thick when you find books on the subject. But for us, that should be enough to give you some idea of what's going on under the hood.